Today we're going to be talking about valence electrons and how these electrons affect the formation of ions. There's a driving force among atoms to gain or lose electrons in order to reach a low energy state, and this state is obtained when an atom has an electron configuration of S2p6 in its outermost energy level. If that happens, it's said to have a full outer shell of electrons. Take, for example, argon. Argon has the electron configuration 1s2, 2s2, 2p6, 3s2, 3p6. So argon has this S2p6 configuration at the end. Krypton is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. So it also has that full S2p6 configuration in that fourth energy level. That D in between doesn't make any difference. It still is considered to have an S2p6 configuration in its fourth energy level. Now let's look at the periodic table and see where those elements fall. If you look at the periodic table, you see that argon is here and krypton is here. So both of them are in what group on the periodic table? Exactly, the noble gases. And we find that the noble gases are incredibly unreactive. They don't react with anything. And a couple of the bigger ones will react under really harsh conditions, but the smaller ones, you won't get them to react with anything. That's because their electron configuration is already where it wants to be at an S2p6 configuration. It's really low. So let's look at why helium is considered to be a noble gas, even though it doesn't have an S2p6 configuration. Well, let's look at helium. Helium's up here. And notice that helium, even though it's up there in the first energy level with a 1s2 configuration, for helium that is full. All you have in that first energy level is a 1s sublevel. So that is why helium is considered to be a noble gas. It doesn't react with anything. So it has a full shell, as we just said. Since it has only the 1s sublevel, in the first energy level. It is full already. So as we said before on this next question, why is it virtually impossible to get a noble gas to react or bond with anything? And that's because it already has an electron configuration that is low energy, full electron shell. It has no driving force to bond with anything. So it already has a low energy, stable electron configuration, S2p6. And that's true for all of our noble gases. We sometimes call that S2p6 configuration a noble gas configuration, as we said up here. So the total number of electrons present in that final sp configuration is very important. These are the electrons that are involved with atoms when they bond with other atoms. So we need a special name for them, and we call them valence electrons. And the number of valence electrons, the number of electrons in that outside sp sublevels, those outside energy level sublevels. It's pretty easy to tell. It's actually really easy to tell if you look at the periodic table. Take barium, that first example, for instance. Barium is right here on the periodic table. And barium, if you notice, is in group 2A. Now, what that means is that Roman numeral tells us that barium has 2 valence electrons. Carbon, on the other hand, if we look back at the periodic table, is over here. Carbon is in group 4A. Remember, we're looking at the Roman numeral, not the regular number, the Roman numeral. And that Roman numeral is a 4. It tells us that carbon has 4 valence electrons. Look at iodine real quick. Pause it for a minute and see how many valence electrons iodine has. Hopefully you did that. And notice that iodine over here, if you look in its up at the top, its group is 7A, the Roman numeral 7A, so it has 7 valence electrons. Those valence electrons are important to us, so important to us that we actually have a structure called the Lewis dot structure that we draw, that we put dots around the symbol of the element. We put the symbol in the place of this X, and we represent the electrons, the valence electrons, with dots. And those dots go in order in the number positions shown here. The first one on the right, the second one on the left, the third one on top, fourth one on bottom, and then we go to the top, 5th, clockwise, 6th, 7th, and 8th. So those are the 8 valence electrons, and if you look at our periodic table, we are looking at the representative elements. So on this table, the yellow and green elements are the representative elements, and those are the ones we're going to be determining valence electrons for. And the maximum number, as you see over here on the far right, is 8 valence electrons, S2P6. So if we're going to draw the Lewis dot structure for sodium, the first thing we need to know about sodium is its number of valence electrons. So we look at the periodic table, and the periodic table, sodium right here. And if we look at the top, we see that sodium has 1 valence electron. So with that 1 valence electron, we draw sodium with its symbol Na in the middle. And as you remember from our example up here, the first electron dot is going to be on the right. So that's the Lewis dot structure for sodium. Beryllium, if we look at the periodic table for beryllium, beryllium is here. It's in group 2A, so it has 2 valence electrons. So those 2 valence electrons for beryllium are going to go first to the right of the symbol, and the second, as we see in our example above, to the left, and that's the Lewis dot structure for beryllium. Nitrogen, here on the periodic table, is in group 5A. Nitrogen then has 5 valence electrons. And looking at the order above, we already know that the first one goes to the right and the second one to the left. The third one on top, the fourth one on bottom, and then we start back up at the top again. The fifth one up at the top, and that's the Lewis dot structure for nitrogen. Oxygen, right here with its 6 valence electrons. We'll have oxygen in the center, 1 to the right, 1 to the left, 1 on top, 1 on bottom. Then we'll start back up at the top and go clockwise. There's the 5th one and the 6th one. So there's the Lewis dot structure of oxygen. Argon, you remember, is at the very end, last column, which tells us that argon has 8 valence electrons, so it has the maximum number of valence electrons. It's going to get all filled up. So right, left, top, bottom, then back up at the top again and clockwise. There's the 5th, 6th, 7th, and 8th valence electron. Now, what I do not want to see is something like this, which I see sometimes. Argon, 1, 2, 3, 4, 5, 6, 7, 8. No, I want it paired up nicely around it. I also see this, argon, and I'll have them dotted out kind of like a star. Looks kind of pretty, but again, neither one of these is what I want to see. I want to see them paired up. If you do this correctly, then if you were to draw an imaginary box around this element, you would see that all of those elements, all those electron dots, end up on the box. So that's what I want to see. Now, helium's a little different. If we look at where helium is on the periodic table, it makes it look like helium has 8 valence electrons. But how can helium have 8 valence electrons if it only has 2 total electrons to begin with? So helium's going to be an exception to the rule. It only has 2 valence electrons. But what we do not want to do is to write helium. Now don't write this first part because it's not correct. But we might start out saying, okay, then helium needs to have 1 on the right and 1 on the left, just like we've done our other elements that have 2 valence electrons. However, this would indicate that it acts a whole lot like beryllium, that it would react like beryllium and do the same things beryllium does, but it does not. So the way we show those 2 valence electrons to show that helium is acting differently is to show that those 2 electrons are paired up on the right-hand side. And that gives us, again, although helium only has 2 valence electrons, it does indicate that helium is a noble gas, that its small sublevel is full with 2 electrons. So, formation of ions. These valence electrons, again, are involved in the formation of ions. When these atoms start to bond, they're going to gain electrons or lose electrons in order to reach a stable, actually a better term would be low energy electron structure. And that noble gas electron configuration, that 8 valence electrons, is that driving force. That's very attractive, and that is why it's referred to as the octet rule. So atoms are going to form ions, either positively or negatively charged. Remember, if they're positively charged, they're going to be called cations. If they're negatively charged, they're going to be called anions. They're going to form these ions by gaining or losing electrons, and let's see how that happens. So look at our first example, sodium. If we draw the electron configuration of sodium, we get 1s2, 2s2, 2p6, 3s1. Remember, the driving force is to have a full outer shell of electrons. So if we're in the 3rd energy level, then our full outside set of electrons would be 3s2, 3p6. But to get to that state from 3s1, we would need to gain 7 electrons. And that's not that easy to do. But think about it. We could also get to that same full electron state, full electron shell state, by getting rid of that 3s1 electron. If we lose that 1 electron, we would end up with a 2s2, 2p6 configuration. It's the 2nd energy level, but it's full, and that would be a lower energy state itself. Electrons are lazy. They're going to go with the least amount of energy involved, and the least amount of energy involved is going to be to lose 1 electron. And remember, since those electrons are negative, if you lose an electron, you're going to become a positive ion, and the sodium ion is the name of that ion. Now remember, we've memorized these charges before, earlier in the year when we were naming and writing formulas for compounds, but this is why it happens. So aluminum, you may recall what the charge on aluminum is, but let's see why aluminum's charge turns out that way. Aluminum is a 1s2, 2s2, 2p6, 3s2, 3p1 element. Remembering that octet rule, we want 8 total valence electrons in the 3rd energy level, or at least the last one. So to do that in the 3rd energy level, S2P6, we would need to gain 5 electrons in order to reach that state. Keep in mind, we could also get rid of that entire last energy level and end up with a full outer shell with a 2s2, 2p6 structure. So if we did that, we would need to lose 3 electrons. Well, what's it going to choose? Exactly, the least number of electrons possible, so it's going to choose to lose 3 electrons. And if we lose 3 electrons, we end up with an ion that has a 3 positive charge, which again, we memorized earlier in the year. And this is the aluminum ion. So let's see something just a little bit different and see what happens with fluorine. So if we look at fluorine, fluorine is a 1s2, 2s2, 2p5 element. If we fill it up to S2P6, I think you can see that we would need to gain 1 electron. Or we could choose to get rid of the entire second energy level, which would leave the first energy level full. But to do that, we would have to lose 7 electrons. Which is it going to choose? Exactly. Gain 1 electron. So if we gain that 1 electron, gain a negative charge, that's going to form fluorine with a negative charge. Remember, we don't put ones in. We don't want to put ones in our charges in formulas or compounds formulas. So F minus for the formula for that ion. And remember, if it's negative, it's going to be the fluoride. We change the ending to IDE, the fluoride ion. So see if you can do oxygen real quick on your own. Pause this real quick and see if you can come up with the number of electrons lost or gained and its charge. So hopefully you looked up oxygen, seeing that it's a 1s2, 2s2, 2p4 element, which if we wanted this to be a 2p6, we would need to gain 2 electrons. Or we could get rid of the entire second energy level, that 2s2, 2p4, but to do that we would need to lose 6 electrons. Which one is it going to choose? Again, yes, the least number of electrons involved. So for oxygen, we would gain 2 electrons. Hopefully that's what you came up with when you tried it yourself. Which would mean that we would have an oxygen with a 2 minus charge, which hopefully remember we memorized those at the beginning of the year. And the name would be the oxide ion, since it's negative, changing the ending to IDE. But we don't have to write out that electron configuration every single time we want to decide what kind of ion these elements will form. Barium, for instance, we looked at barium to begin with. Barium was down here with its 2 valence electrons. So it had 2 valence electrons, so its structure, its Lewis dot structure, looked like this. When we decide how many electrons it loses or gains, the magic numbers are 0 and 8. So it wants to gain up to 8, or it wants to lose down to 0. So in this case, our 2 choices for barium would be to lose down to 0, which would be to lose 2, or to gain up to 8, which would be to gain 6. And we, again, always go with the least number of electrons involved, so that would be losing 2 electrons. If we lose those 2 electrons, we're going to form a +2 charge, and the ion symbol would be Ba2+. Notice that the charge is written with the sign first, the number second, whereas the ion symbol is the Number first, sign second. So please get that right. Sulfur, if we look for sulfur on the periodic table, we see sulfur right here. And sulfur has 6 valence electrons if you look at the top of its column, which means it's going to look like this. Notice that if sulfur lost those electrons, it would have to lose down to 0, lose 6, or it could fill in those gaps and gain 2. It's going to choose the least number, so gain 2 electrons is what it's going to do. It's going to be the least energy involved. That forms an ion that's -2 in charge. The sulfide ion then would be S2-. So pause this real quick and try nitrogen and potassium on your own. So hopefully you did that. Hopefully you looked at nitrogen and saw that it had 5 valence electrons. We've done that one before. So its Lewis dot structure would look like this. And hopefully you decided that it would be much easier to to gain 3 electrons than to lose 5. So gain 3 electrons, which would mean that its charge would be a -3 and its ion symbol would be N3-. Potassium, being in group 1A, is going to have 1 valence electron, so it's going to look like this. It could lose that electron, that 1 electron, or gain 7. It's going to lose 1. Much easier to lose 1 electron. If it loses that electron, it will be a +1 charge. When we put it in a symbol or formula, remember, we don't put those 1s in, K+. So hopefully that's what you got. Now, carbon's a little bit different. Carbon, if we look carbon up, we've already seen that carbon has 4 valence electrons, so its Lewis dot structure would look like this. Now, its choices, think about it, it would need to lose 4 or fill in the gaps by gaining 4. So which one's it going to choose? Well, it can't really choose either. Carbon happens to be the most versatile element on the planet in that it can form those different ions, it can form different kinds of bonds where it doesn't lose or gain electrons, it shares them, long chains of molecules, of carbon atoms and molecules, all kinds of things that carbon can do. So we're going to have to put both if we're talking about electrons lost or gained. So we're going to have to say that carbon can either lose 4 electrons or gain 4 electrons. So we're going to be able to say that it could form a +4 ion, it could form a -4 ion. So C4 plus and C4 negative. We could see something like that. That plus didn't turn out looking very good, but neon, on the other hand, neon is going to have 8 valence electrons, so it's going to look like this. And if you notice when you get done, all the spots are filled in. It wants to gain up to 8 or lose down to 0. It's already at 8. So what's it going to do? Absolutely nothing. It's not going to gain or lose any of the electrons. It's a noble gas. It has no driving force to form an ion. It's not going to form a charge. Technically, this is not applicable because neon won't form an ion symbol, but if you put Ne with a 0 charge there, that would be acceptable. Helium, watch out for helium. Remember, helium is an exception to the rule. It looks like it has 8 valence electrons in that last column, but it actually only has 2. And remember how we write the symbol for helium with 2 electrons on the right. So helium, is it going to gain or lose electrons? It looks like it would lose 2, but remember, it's a noble gas. Is it going to do anything? No. It's going to have 0 for its gain or loss of electrons, 0 for a charge. Again, not applicable as far as ion symbol, but if you put He0, that would be acceptable. Now, at this point, the rest of this discussion is for extra credit, so if you want to stop listening at this point and go on with your worksheet or assignment, you can. But if you're an AP, going to be an AP, I would suggest going ahead and doing this. The electron configuration of ions. So let's say we have S2 minus. Normally sulfur, we've already looked at this, normally sulfur would have a 1s2, 2s2, 2p6, 3s2, 3p4 configuration. But since it has that negative 2 charge, that tells us that it's gained 2 electrons. So if that's true, we're going to need to change this electron configuration to show that. So we're going to put 3p6, which shouldn't surprise you. The driving force to form an ion is to reach that stable S2p6 configuration, and that's exactly what sulfur did. So look at sodium. Sodium is in the same situation in that normally it has the configuration of 1s2, 2s2, 2p6, 3s1. And the same situation in that it could, in the processes of forming an ion, reach a lower energy full outer shell state. How does it do that? It does it by losing 1 electron. Since it's a +1 charge, that means it has lost 1 electron. Now, the way I want you to show this, some people show it by completely getting rid of that 3s1 sublevel shown. What I would like for you to do is to put a 0 there instead and put that in parentheses, showing that it used to be there, but it's disappeared now. I just think it looks more like an ion there instead of looking like just the electron configuration of neon. The last two are a little bit different. These are these are transition metals, and transition metals form ions by losing electrons a little bit differently than the other elements do. Iron is 1s2, 2s2, and this is true for all transition elements. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. And since it's a 3 plus ion, that means that iron has lost 3 electrons, so it's lost 3 electrons. And the weird thing about transition metals lose electrons first from the S sublevel. And if there are any more electrons to lose, then they'll come from the D. So transition metals lose electrons from the S sublevel first, when they form ions. So what does that mean? It means the first thing that's going to happen is that these 2 electrons in the 4s are going to be gotten rid of. Keep in mind that when we lose those electrons, I like for it to be put in parentheses. That S sublevel is not there anymore, but I want to show that it used to be. And we're going to move down now. We've lost 2 electrons. We still need to lose a 3rd electron, so we'll drop that 3d6 down to a 3d5. And that's the electron configuration for the iron 3 ion, Fe3+. Tin will do the same thing. Zinc will do the same thing. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10 is a normal electron configuration for neutral zinc metal. But when it forms an ion, since it's 2+, we can see that it has lost 2 electrons. Where are those electrons going to come from? Exactly, from the S first, so we're going to get rid of those. And since it only had 2 electrons to lose, we don't need to take any from the D. So this would be the electron configuration for the zinc ion.